Hi, I'm Rich Booman, a hardware engineer at Tektronix. In this video, I'm going to show you how to demonstrate the IsoVu measurement system using the IV Demo demonstration kit. This demo showcases the superior common mode rejection capability of IsoVu and its ability to make accurate measurements on current sense resistors. This video and the scripts that go with the demo will highlight the key IsoVu specifications and provide a comparison to existing products. The three expected outcomes of this video are: 1. You should feel confident in performing an IsoVu demo. 2. You should be aware of how the features of IsoVu map to customer pain points. And 3. You should understand how to ask selling questions to create opportunities for demoing IsoVu. To run the demo, you only need the demo kit, a TechVPI oscilloscope, and an IsoVu. You don't need any other equipment. The demo board includes a high voltage power supply and pulse generator. There are circuits for demoing differential response, common mode rejection, and the use of current sense resistors. The kit has two accessories: a power adapter and an SMA cable. The SMA cable attaches the pulse generator output to one of the demo circuits. One of the revolutionary yet least understood features of IsoVu is its common mode rejection, with a ground-breaking 120 dB or 1 million to 1 common mode rejection ratio. CMRR is a critical but often overlooked specification and is a major customer pain point. The objectives of this demo are to better understand the common mode rejection specification, how poor common mode rejection can affect the measurement, and how IsoVu has superior performance to traditional probes such as the TMDP-0200 and the TDP-1000. Let's briefly review a few concepts. The user's primary goal is to get an accurate differential measurement. Typically, differential measurements are made with a differential probe. Differential probes are based on difference amplifiers, which measure the potential difference between two test points. If the voltage at A is 2 volts and the voltage at B is 1 volt, the output is the difference between A and B, which is 2 minus 1, or 1 volt. So if the inputs to the amplifier are connected to the same signal, what would you expect the output to look like? If this is an ideal amplifier, you would expect the output to be a completely flat line, or 0 volts, because the amplifier should completely subtract the signals at inputs A and B. The signal that is common to both the non-inverting input and the inverting input is referred to as the common mode signal. An ideal difference amplifier would reject 100% of the common mode signal. If you have 50 volts on input A and 50 volts on input B, an ideal differential probe would have an output of 0 volts. It's 50 minus 50. When you're making a differential measurement, the only thing you want to see is the difference between the two signals you're trying to measure. You shouldn't see the effects of common mode voltage at the output of the amplifier. So if I'm trying to measure 2 volts differential when there is 50 volts of common mode voltage, the probe needs to display the difference between 52 volts and 50 volts, which is 2 volts. The ability to reject the common mode signal is the amplifier's common mode rejection ratio. Ideally, an amplifier would have an infinite CMRR. The higher an amplifier's CMRR, the less impact the common mode input voltage has on the differential measurement. Because it's impossible to perfectly match the two inputs of a differential probe, every differential measurement will include some common mode error. It is only a question of how much. It's also important to note that an amplifier's common mode rejection ratio is frequency dependent. Differential probes typically have higher CMRR at DC and low frequencies, but the CMRR degrades as the frequency increases. If your differential signal has a 50 volt common mode voltage with some high frequency content, how much error should you expect? Given IsoVu's 1 million to 1 rejection ratio at high bandwidth, you would divide 50 volts by 1 million. That's about 50 microvolts of error. The previous best-in-class differential amplifier, the LaCroix DA1855A, has a CMRR specification of 20 dB at its listed 100 MHz bandwidth. That's only 10 to 1. With this amplifier, the 50 volts of common mode voltage would only be divided by 10, resulting in 5 volts of common mode error. Because of the frequency dependence of CMRR, Most differential probes only list the CMRR values at DC and low frequencies on the datasheet. Let's examine some examples from Keysight and LaCroix. First, we'll take a look at the Keysight N2790A high voltage differential probe. It's a 100 megahertz probe, but when we zoom in on the numbers in the datasheet, it only specifies values at DC, 60 Hz, 1 kilohertz, and 1 megahertz. It seems strange that the datasheet doesn't include the CMRR value for 100 megahertz since that's the listed bandwidth of the probe. When you look at the CMRR plot in the manual, it becomes clear why the higher bandwidth values are omitted. At 100 megahertz, the probe only has 27 dB CMRR, which is about 22 to 1. Going back to our example of a 50 volt common mode voltage, that would be 50 divided by 22, which is approximately 2 volts of common mode error. A similar story is true of the LaCroix DA1855A differential amplifier. The front page of the datasheet calls out a CMRR value of 100,000 to 1, but doesn't say for what bandwidth. Once again examining the CMRR plot in the manual, the CMRR at 100 megahertz is 20 dB. That's 10 to 1, and for our previous 50 volt example, that's 5 volts of error. Now let's go back to the demo board. Because many measurements are made on signals with a reasonably fast edge rate, on the demo board we've included a high voltage pulse generator. The repetition rate or switching frequency of the pulse generator is 10 kilohertz, but the edge rate is 500 picoseconds, which corresponds to a bandwidth of 700 megahertz. This is typical with switching waveforms. The bandwidth required to accurately measure the edges will be much higher than the switching frequency. The demo board has a fast edge that will allow you to demonstrate the difference in performance between IsoVu and other differential probes. The high amplitude output of the demo board is approximately 50 volts with an edge rate of 500 picoseconds. Because the 50 volt output exceeds the common mode capability of the TDP-1000, which has a 35 volt common mode voltage rating, the demo board includes a 2x attenuation section. The 1x attenuation has an output voltage range of 50 volts, and this part should be used to compare against higher voltage probes such as the TMDP-0200. The 2x attenuation has an output voltage of about 25 volts, and this part should be used to compare against lower voltage products such as the TDP-1000. Press Default Setup on the scope. Now make sure that the power supply is turned off to the demo board, and connect the SMA cable from the high amplitude output connector J73 to the common mode 1x attenuation connector J23. Now we're going to connect the TMDP-0200 to channel 1 of the scope. Set the TMDP-0200 to the 75 volt range. Connect the probe tips together and perform the auto zero operation on the scope. Now we're going to twist the leads together several times and connect the hook clips to TP10 and TP27. So these test points are connected to the same signal on the scope, so it's a common mode signal. Set the vertical to 500 millivolts per division, horizontal to 40 nanoseconds per division. And now we can power on the demo board. Now we're going to set up a scope measurement to measure the peak to peak. We should also turn averaging on. Ideally what we would see is a zero signal, a flat line. What we're measuring on the scope right now is 2.4 volts peak to peak. Now looking at our common mode rejection ratio calculation, this gives us a common mode rejection of approximately 2.4 divided by 50, take the log, multiplied by 20. So right now what we're seeing is a common mode rejection ratio of about 26 dB. That's worse than 20 to 1. And you can see as we move the cables around that the signal changes significantly. So depending on exactly where the probe is positioned and the lead dress, the signal can change from less than 2 volts to almost 4 volts, over 4 volts. So now to compare to IsoVu, we need to turn the demo board off, disconnect the leads, disconnect the TMDP from the scope. The next step is to connect the IsoVu to channel 1 of the scope and wait for it to finish its power-up sequence. Then put it in the 1x range, which is the more sensitive range, and push the self-cal button and wait for it to finish its self-cal adjustment. Once that's complete, we can connect the IsoVu tip cable to the connector at J25 and turn the demo board back on. With IsoVu, the common mode signal is much smaller, so we will have to adjust the trigger level. So now you can see that we're no longer triggering. There's not enough common mode interference from the demo board to trigger the scope. Now if we adjust the vertical scale of the scope down from 500 millivolts where it was with the previous probe down to 10 millivolts per division and adjust the trigger level, we can finally get a signal that we can trigger on. But this signal is just a little bit of power supply pickup from the controller board. At this point, if you turn the demo board on and off, you can see that this signal remains on the scope. So this 10 or 20 millivolts of signal that we're seeing now is just due to the power supply pickup. The same common mode rejection lab procedures can be followed for the TDP-1000 by connecting the SMA cable to the SMA connector J54 labeled common mode 2x attenuation. Let's examine an example where common mode interference can pose a measurement challenge, the half bridge. All power applications need to convert electric energy efficiently. A commonly used topology to accomplish this efficiency goal is the half bridge. The half bridge circuit consists of an upper and lower switch, which are typically MOSFETs. This circuit includes a supply voltage, a midpoint between the two switches referred to as the switch node, a ground return, and a low side gate drive input and a high side gate drive input. To better understand why common mode interference can prevent an accurate measurement, let's investigate where the common mode voltage comes from. To do that, we will briefly explore how the half bridge works. The required voltage is applied at the high side gate and turns on the upper switch, connecting the switch node to the supply voltage. The switch node is now at 50 volts, and the high side gate drive voltage required to turn on the switch is 2 volts above the switch node. Now the upper switch turns off and both switches remain off during a short dead time. The switch node voltage starts to decrease. The dead time ends and the lower switch turns on. The low side gate voltage is at 2 volts reference to ground. Turning on this switch forces the switch node voltage to ground. Next, the lower switch turns off and both switches remain off during this dead time. Finally, the high side turns on again and the cycle repeats. During this single cycle, the switch node transitions from 50 volts to ground and then back to 50 volts. Because the high side gate voltage is measured relative to the switch node, and the switch node transitions between high voltage and ground at a fast edge rate, this common mode signal can interfere with the ability to measure the signal accurately. When the switch node is at 50 volts, and given that the required high side gate drive input voltage must be 2 volts to turn on the switch, that makes the gate voltage 52 volts. The measurement challenge is to measure 2 volts differential in the presence of a 50 volt common mode voltage. Remembering our previous example of measuring 2 volts differential in the presence of a 50 volt common mode voltage, this measurement can only be made using a probe with high bandwidth, high common mode voltage range, and a high common mode rejection. A higher CMRR will reject more of the signal that is common to both test points. In this case, you want to reject the 50 volts of common mode voltage and only see the 2 volts from the gate to the source. While it is important to measure both gate voltages, most designers only measure the low side gate voltage because they think the measurement is ground referenced and only requires a high bandwidth passive probe, not a differential probe with high CMRR. They believe the measurement to be accurate when it probably isn't, so designers will measure here and infer the measurements to the high side. IsoVu is the only measurement system in the world that can measure the high side gate on a half bridge because of its high bandwidth, high common mode voltage, and high CMRR. So what are the key things you should understand about common mode rejection ratio? 1. Every measurement might include common mode error. The amount of error depends on the probe's CMRR specification, the common mode voltage edge rate, and the common mode voltage amplitude. 2. Every differential probe's datasheet will boast a large CMRR value at DC and low frequencies. You will probably have to look in the manual to find the complete CMRR specification. 3. Match the required CMRR to the signal's edge speed. The device may have an operating frequency specified in kilohertz, but the rise time of critical signals may occur in nanoseconds. What questions can you ask based on this information? 1. Are you measuring differential signals in the presence of common mode signals? Do these signals have fast edge rates? Anything faster than 100 nanoseconds would qualify as fast. Are you having difficulty making measurements because of common mode signals? Are you satisfied with your high side gate measurements? Are you able to optimize and tune your circuit given the presence of common mode signals? Traditional current probes have insertion inductances of several nanohenries or more, depending on the current probe used, wire gauge, and wire length. When I add a loop of wire into a circuit like this one so that I can attach a current probe, it's going to add at least 1.5 inches in length. This translates to about 30 nanohenries of inductance. This will have an impact on circuit performance. Some disadvantages of current probes are that many designs cannot tolerate the additional inductance of the current loop, and traditional probe heads are big and you may not be able to get one into the design. When a traditional current probe cannot be used due to added inductance, users typically turn to a sense resistor. A small value resistor used as a current sense resistor will have less impact on circuit performance than a conventional current probe due to the smaller series inductance possible with a current sense resistor. To get the current value, the voltage is measured, and given the known value of the sense resistor, math can be used to derive the current. The problem with using a current sense resistor is that you're trying to measure a small differential voltage across the sense resistor in the presence of large common mode voltages which may have high frequency content. This measurement requires a differential probe with high bandwidth, high common mode voltage, and high CMRR. Otherwise, the differential measurement is going to get swamped out by the common mode interference. Remember the last section on CMRR. If you have volts of error due to poor CMRR, trying to measure millivolts across a current sense resistor is impossible. In the lab, the pulse generator will generate a pulse of about 50 volts. Across the 50 ohm load, this implies a current of about 1 amp. The sense resistor we're using on the demo board is 250 milliohms. With the 1 amp current, this will generate a 250 millivolt signal across the current sense resistor. There are two different current sense resistor measurements on the demo board: the high side current sense resistor and the low side current sense resistor. On the low side current sense resistor, the voltage is measured reference to ground. The differential measurement across the resistor is 0.25 volts minus 0 volts. The differential measurement should give you about 250 millivolts. For the high side, the differential measurement is not ground referenced. We're going to measure 50.25 volts minus 50 volts. In this case, the additional 50 volts is the common mode voltage, which we want to reject so that we only see the 250 millivolt differential voltage drop across the sense resistor. For this section, we will once again follow the procedures included in the lab guide. And now connect the SMA cable from the high amplitude output to the high side current sense MMCX SMA connector J5. The IsoVu connected to channel 1 of the scope. We'll connect the probe cable to the MMCX connector on the high side current sense MMCX section of the demo board. Set the scope to averaging. We'll set the vertical scale to 250 millivolts per division and the horizontal scale to 4 nanoseconds per division. Now we'll power on the demo board and adjust the trigger level. So now we're triggering on the voltage from the current sense resistor. We'll adjust the vertical position to center the pulse on the screen. We can adjust the horizontal scale to see the full duration of the current pulse. Now there's a couple of things to notice here. One is this leading pulse at the front edge of the output waveform. This is due to the inductance of the current sense resistor. These current sense resistors are very low inductance, but still it has enough inductance to cause this spike. The current sense resistor inductance is less than a nanohenry. You can imagine how big this spike would be if you used a regular current probe, which had 30 nanohenries of series inductance. The other thing to notice here is this flat level right after the leading edge of the current pulse. We can use the cursors to measure that level. We'll bring the cursors onto the screen. They're on the waveform. So you can see that this voltage level is being measured with the cursors at about 260 millivolts. 260 millivolts through the 250 milliohm sense resistor gives us a little bit more than 50 volts. So this is a fairly accurate representation of the current pulse that we have through our current sense resistors. We'll pull up the cursor menu and select horizontal cursors. Then we can adjust the level to measure the amplitude of the current pulse. And looks like the current pulse is giving us a signal of about 260 millivolts through our 250 milliohm sense resistor, so that corresponds to about an amp through the current sense, a little bit more than an amp through the current sense resistor. So now we're going to shift over to the TMDP0200. We're going to need to use the different section of the demo board. We're going to use the current sense resistor that has test points. So I'm going to turn the demo board off and move the cable. We'll remove the IsoVu probe from the demo board. Move the SMA cable to the current sense test point. So now we're going to do the same measurement on a high side current sense resistor using the TMDP0200 probe. So we'll plug the 100 into channel 1, set it to 75 volts, do an auto 0. Now we'll connect the probe tips to the test point with the positive or red probe going to the sense plus test point and the black probe to the sense minus. Then we can turn the demo board back on. Now you can see the waveform that we're getting from the TMDP0200. Now this time base is set to 40 nanoseconds, the vertical scale is 250 millivolts. The cursors are still about where I left them before, set at about 250 millivolts. Now you remember with the IsoVu probe, it was very clear where the current pulse was. The current in this setup is still the same. It's still 1 volt, 1 amp through a 250 milliohm sense resistor. So the current pulse is in here somewhere at about 250 millivolts. And you can kind of imagine a 250 millivolt signal there. But in the presence of all this common mode error, it's really impossible to make that measurement. So you might wonder what it looks like if we move one lead over to the other side. So we'll just turn the board off and connect both leads to the same test point. We'll turn the demo board back on, and you see we still have this same huge common mode error. Now there's the same test point, V1 minus V2, it should be 0. It's the same input on both sides. We get this huge common mode error. So you can see, I mean, this peak-to-peak error is a couple of volts. It'd be impossible to make a 200 millivolt measurement with this kind of a test system. So what are the key things you should understand about current sense resistors? 1, the measurement is always differential. You're always measuring the voltage drop across a resistor. 2, depending on the location of the sense resistor in the circuit, there could be very high common mode voltages on the test points. 3, to reduce the impact on circuit performance, the sense resistors have as small a value as possible. The measured signal across the sense resistor will likely be very small, on the order of millivolts. 4. Poor common mode rejection performance will lead to common mode errors of several volts or more, which makes this type of measurement impossible. So what questions can you ask based on this information? 1. Are you measuring currents in the presence of high-frequency common mode voltages? 2. Are you having difficulty making measurements because of the high insertion inductance of a conventional current probe? And 3. Are you satisfied with your high side current measurement? There are 3 sections of the demo board we didn't discuss. The differential and 2 low side current sections. The differential section is not intended to highlight the features or benefits of IsoVu, but was only included to prove that there is actually a differential signal present. The reason why it was necessary to show the differential signal was due to the fact that IsoVu's common mode rejection was so good, early customers didn't believe the signal was present. The procedures for demonstrating the low side current sections are the same as the procedures for the high side sections. We included the low side sections because this is often where users will measure current sense resistors. They measure the low side because it's impossible to make a current sense measurement on the high side. Using these sections of the demo board, you can compare the low side ground reference measurements to the high side non-ground reference measurements using IsoVu or a customer's probe. The IV demo kit is available through your normal demo acquisition process. More information about IsoVu can be located on the Isolated Measurement Systems page on tech.com under Probes and Accessories, or by searching for IsoVu.